Okay, folks, I'll just give a couple of words on Dr. Pillay, who's with us. At the last meeting, Lloyd broached the subject of Dr. Pillay presenting this work to us, and it was quite relevant because she's done, I think, a good body of work in trying to estimate the impact of EV charging on electricity consumption in the residential sector. And that's always been an unspoken question for us. You know, EV batteries are possibly 10 times the size of a normal dwelling solar PV battery in a dwelling. What is the impact of this going to be with rising levels of penetration in domestic households? What we've seen is that EV penetration is increasing rapidly in South Africa, and every time you get an estimate of it, it's supposedly more, so it's accelerating. And recently, I think it was yesterday, Minister Patel said, yes, there will be incentives for the electric vehicle industry in South Africa, and we must expect penetration to increase. And so the question is, you know, is our network ready for it? Or can we get our network ready for it? And what's the impact likely to be? What must the network be ready for? And Dr. Pillay is the person that can tell us this. So that is what her work is about, and the important work, I think, to us nationally. Pillay is a corporate specialist in system dynamics at Eskom. She graduated with an engineering degree at Wits University, and she worked at a production engineer in the steelmaking industry. She joined Eskom's research business unit, where she's involved in generation plant research. And she's currently a corporate specialist. She's authored many internationally recognized papers. She has a book behind her name on system dynamics simulation modeling. And she's a guest lecturer at various universities. She's also a founding member of the South African System Dynamics Chapter, and has held the post as president of that chapter for several years. So there's no doubt that Dr. Pillay is equipped to advise us on the effect of EV charging on the electricity sector in South Africa, but she's also equipped to speak in great depth on system dynamics modeling. So let's just appreciate and respect what we have in front of us, and think up really difficult questions as she speaks. Dr. Pillay, I give the floor over to you. Thank you.
Thanks, Marcus. So what I'm going to do now is I'm going to switch off my camera to save some bandwidth. And thank you to everyone for the opportunity to present today. I did the work is, for all intents and purposes, complete in terms of this phase, but it still actually needs calibration and validation through various engagements before it's something that can be published or shared widely. So the presentation title, we're just going to look at some results that were obtained after modeling EV charging impacts on the electricity consumption profiles in the residential sector. And of course, the method used was system dynamics. The content will go around simulation and optimization modeling and the basic differences, a little bit on the history of system dynamics as per Marcus's request, and then we'll get into the background and objectives of the research, followed by a little demo. so that we can get some insight into the tool that was developed. We'll look at some results and conclusions. So just a little bit in terms of optimization and simulation modeling. When we look at a system problem, we look at it through different lenses. When we have this linear view of the world, we have information about a problem that allows us to take a particular action, and of course, a result emerges. Then we move on to the feedback view of the world, but it's still a closed loop feedback. So you have information about a problem, you take a particular action, a result emerges. However, you have to then revisit what you originally had in terms of your knowledge about the problem. And again, you may have to amend or take a different action. And of course, you may receive or you may end up with a slightly different result. When you look at the closed loop feedback view of the world, and this is the important thing, the unintended consequences. You have information about the problem, you take a particular action, a result emerges. However, what you have then happening is that the environment changes. And when the environment changes, your information may change drastically because then you have more factors that are then affecting the initial environment in which the system problem might have occurred. You are then forced to take a particular action. However, the environmental change has then resulted in what we call an unintended consequence that we wouldn't otherwise have been aware of. And so with system dynamics modeling, you're looking more at this closed loop feedback view of the world with the unintended consequences. And with optimization modeling, you're looking more about a relatively linear view of looking of approaching a problem. And so when you have things like Plexos modeling or other models that really try to get a least cost solution, that generally falls in the optimization realm. When you have models that can create various scenarios where you can do sensitivity analysis, and it's very descriptive as opposed to prescriptive, then you're talking about simulation, and that's more where my sort of modeling lies. In terms of where system dynamics actually came from, it was originally founded by Professor Jay Forrester. He was a lecturer at MIT, and he had an electrical engineering background. But what he thought is, because he was asked to run the management school of technology at MIT, he then thought, what if I actually use my background in electrical engineering and compare it and combine it with my management experience, and then try and see how we can get value from these two areas coming together. And his very first challenge was when General Electric actually contacted him and said, listen, we have a problem. When we look at the last few years, we find that there's a issue when it comes to our employment. It seems as if it's following the external business cycle, but we're not sure because looking at that, there's no real correlation. And so Jay Forrester then came up with this hand-drawn picture or hand-drawn stop flow feedback diagram. And with this, they actually try to analyze the problem and realize that, listen, the problem is actually due not to the external business cycle, but actually due to the internal policies of the company, and there's a whole long story behind this, which I won't get into, but essentially this was the first application of system dynamics, which is really all about your stock flow feedback structures. This is just on the top right, one of the a very basic structure showing some of the types of elements that are included in the model, where you have the stock, which can deplete or accumulate depending on the net outcome of your inflow and your outflow. And in terms of the definition of system dynamics, it's basically a computer simulation method. It allows decoding of your complex system problems. It incorporates and links the underlying system structures to what we perceive to be the behavior, and uses systems thinking principles so that we can understand what the root causes are, and thus impact or identify levers to initiate change and to address the fundamental problems of the system. This is the book that we actually published in Eskom, linked to all of the system dynamics projects that we have tackled since 2010, when we first started using system dynamics, and handled a lot of Eskom-related problems. This particular project was actually done for a letter. And the reason why it was initiated and carried out was really when we looked at the residential sector, we realized that the electricity consumption is relatively large. If you look at it, 19%, compared to the remaining sectors, excluding the industrial sector, is really quite a significant value. And so any dynamics that affected the electricity consumption in the residential sector could actually affect our planning when it comes to, the load profiles and what we think would be consumed due to solar PV or electric vehicles and related technologies. So in this particular project, what we realized is that, yes, we do anticipate that there's going to be a large number of electric vehicles in the future. However, if a lot of the charging then takes place in the residential sector at home, how does this affect not just Eskom in terms of additional sales, and how much more electricity do we then need to plan for? But it also then is interesting in terms of the consumer side of things, because of our increasing tariffs, because of load shedding. There's always all these fears that, listen, if I buy an electric vehicle, can I actually, will I be able to charge at home? How much is it going to cost me? How much of energy will I consume through my charging systems at home? And so we thought, let's try and better understand this. In the past, when we did some analysis in terms of electric vehicle market penetration, I built an annual resolution system dynamics model. And so we've never done this on an hourly level. So it was something new that we thought, if we actually get this right, it will actually be quite interesting to understand all the various dynamics, some of which you'll find is listed here in terms of the research questions, like what are the energy costs when you charge your electric vehicles and you actually have then different residential tariff options. What happens if you have an AC charger, a DC charger, on your EV fuel cost, when you compare that then to your internal combustion engine fuel costs, does it actually make financial sense to go for then your EVs if you are going to charge these at home or using public chargers? Also trying to understand, the seasonal impact for your tariffs with respect to your electric vehicle charging. We did look at the time of use tariffs, and to see, would this potentially change charging behavior to discourage peak charging? And the premise was that in every household, we're all kind of looking to optimize our overall electricity bill. So will we actually move to a cheaper charging time if we're going to save a few rands? And so the question was, but how much would we be able to save? And, is that significant enough to change customer behavior in terms of when people start charging their electric vehicles? And then the other things that we looked at was if some households install solar PV, what would that mean on a national level in terms of how much of potential sales does Eskom lose, but also, how much less gigawatt hours do we need to then plan for that we originally, did not have line of sight of. And then, looked at different load shedding stages and charging and costs. And we chose one municipality just to compare that, the municipal tariff with the two other tariffs, which was the home flex and the home power tariff, and compare that to each other. Now, before I carry on, my presentation, what I'm going to do is share. So this is the software that I use. So Marcus did say that maybe I must do just a very quick demo in terms of how the software works, so that when you see the gory bits in my model, you'd kind of understand really where we were coming from. So this is, yes, like, wow. I'm not sure why that happened there, but this is my stock that I spoke about. And let's assume the stock is actually a bathtub. We have an inflow, right? And we have an outflow. The inflow would be the tap, and then the outflow would be our drain. And then we would have a converter, which could be time series information or a constant in time. And then this would just be the rate of inflow. And then we'd have one that says this could be the rate of outflow. In this particular case, what I'm going to do is I'm going to assign a constant to them. And these pink lines are basically what we call connectors. So the connectors carry information from one variable to the other variable. And of course, we've got all these warning signs because we haven't assigned values. And so what you find here is that we can put in equations. In this case, I'm going to say this bathtub has 50 liters of water. You can enter a unit. I'm going to say the rate of inflow is 0.5. My rate of outflow is 0.1. My equations here would be my rate times the volume that I have in my bathtub. And on the outflow side, it's a similar story. And so this is one of the structures now that we've built. What we can then do is put down a graph. And what you'd find is in the software, I meant run specs. In the software, you find that you can define what your integration method would be and your time steps. In this case, we're saying, listen, perhaps we're talking about 13 hours. I know it says months, but let's say it's hours or minutes or seconds. But you can then define that. And then you can put your initial graph here and we can make it comparative. So when we run the model, you'll find that we can then run different scenarios and change our variables. If I increase the rate at which the inflow is taking place, it's going to obviously fill up a lot faster. And if I increase the rate at which it's flowing out, it's then going to deplete a little bit faster than what it initially was. And that, in a nutshell, is basically what the software does. And so, I was actually intending to go into the software and carry on with showing the model. So this is then the model for the EV impact in the residential sector. Find it's relatively large. Not one of the biggest that I've built, but this is the stock flow feedback structures. There's a lot of them. And then if we look at the interface, the interface is usually a blank, page. And depending on what the customer wants, we pull out certain variables onto the interface from the model structure so that we can engage with these and run different scenarios. In this particular case, all of these were actually then built for Aletta and her team. I'm going to reset it and explain to you what's actually in this model. So for this particular project, it was divided into two parts. We have a single household and looking at all of the dynamics within the single household. And then we had the national side of things. Now, it was important for us to understand both levels. If you're looking at a single household and you change certain variables, what's the impact on how much more that household will consume in terms of electricity? But also nationally, when we look at larger volumes of electric vehicles and larger volumes of solar PV being installed, what does this mean in terms of are we prepared with our planning? So what you're looking at here is the different quintiles. So what I've done is I'm going to just go back here quickly. The households were actually divided into 5 quintiles. They all linked to the incomes for these different households. So the quintile 1 was your chronically poor, quintile 2 your transient poor, quintile 3 your vulnerable middle class, 4 is your stable middle, and 5 is your elite. So the assumption for this particular project is that your stable middle and your elites are the ones that could afford your solar PV and your EV purchases. And on a national level, then this distribution became important. So going back here. So when I say quintile 1 and quintile 2, that's basically linked then to the income distribution. This is quintile 3 and quintile 4 and quintile 5. So the time resolution, I said it was hourly for about 744 time steps, which is effectively a month. So when you run it, what you see at the end of a run is basically over the period of a month. So in this case, if we say we're looking at the January energy consumption profile, we run it, and you find this is what it looks like for all of the different quintiles. And then what we also have as a possibility is looking at the EV charging, setting or looking at our tariffs, load shedding, solar PV, and batteries. So how this actually works then is, if we go to our EV charging, and this is still for a single household, we can then say, listen, we want to then, over that January energy consumption profile, we want to include an electric vehicle. In this case, it's going to be a full battery electric vehicle. We're going to charge it starting at 6 p.m. every day, or we can make it every second day, or we can start, at 1900 hours every second day. And so we can actually set these values where we want to do an evening charge, or we can, or we can include a top-up charge in the morning to start at a certain time and say, listen, every 2 days, quickly want to charge the car and get going. So when we do that, we'll find a slight increase. If you go back to household consumption, these graphs are a little bit bigger. And you'll see there is a little increase in terms of the energy consumption, because we are then consuming more energy through charging at home. So all of those variables can be set. So already you can see the type of scenarios that you can come up with are numerous. And of course, you can then also select the battery size. So based on the income, we figured that the quintile 4 are most likely going to be able to afford to purchase a small electric vehicle, and your quintile 5 would most likely settle on a medium EV. They could potentially afford a large EV, but you have to print down some variables and assumptions if you want to start running these scenarios. And so if we say it's a small electric vehicle, I've set it at 40 kilowatt hours in terms of the full battery, but I could reduce it if necessary, or increase it. And that's the thing about a simulator. You can run that many more permutations. And then I've also introduced looking at the different tariffs. So here we've got the option of the home flex tariff, which is more the time of use tariff, or the home power tariff, and that's a local authority and non-local authority, which have slight differences. And then we actually ran scenarios to see what that impact would be at the end of a month in terms of the cost for that particular household. So if I ran, for example, a February profile, I would get a different cost, but I would also then get a different consumption profile here. I just want to change this so that we can actually see what's happening. Else you can't actually see the pattern of behavior. And so we also introduced an option to have load shedding in the scenarios where if we did include load shedding, we can include different stages. And say, if we had stage 1, perhaps it's for 2 hours over 2 days, starting at 6 a.m. And similarly, we can then stipulate, which load shedding stages we want to introduce to run a particular scenario. And of course, when we run that, you'll find that it's literally going to knock out the power at the times when we are load shed. And then the simulator then also allowed us to go and select a different solar PV capacity. The options were 2 kilowatt system, 3, 4, 5, or 10. And based on what the information we received from one of the OEMs, they were like, for Quintal 4, it's generally a 3 kilowatt system that people would look at. Whereas for Quintal 5, on average, it's more like a 5 kilowatt or less system. They haven't seen very many more than 5 kilowatt solar PV systems. And of course, this is a generalization. It's not something that is fixed in terms of assumptions that can be used. And once you select the particular PV system that you want to run your scenarios with, you can also then adjust the performance ratio variables because there's equations behind here that allow us then to calculate the energy generated through the solar PV system per hour, depending on the capacity of solar system that you have. And besides that equation, we've got another equation built in here that allows us to calculate the levelized cost of the PV panels, as well as if we had to have batteries and inverters. And I must say up front, the charging of the batteries and the inverters is not reflected in the graphs or in the model structure. The reason for including that was actually just largely for the purposes of calculating this levelized cost of solar, inclusive of the costs that come with batteries and inverters. And when we say we want to run or we want to introduce our solar system for Quintal 4 and our solar system for Quintal 5, we can have an option of running a scenario that says that we do have a battery. And when we say we have a battery, the assumption is that you have a consistent energy generation through the solar PV system. Or if it does not have a battery system, then the assumption is that you only have solar energy generated during the hours when the sun's shining. And so we get to the national household consumption picture. And in terms of the national household, now this becomes important when we talk about our vehicles. So this was the 2022 situation. Looking at it, I mean, we had about 1,357 full batteries, 8,700 odd hybrid electric vehicles, and we had about 824 plug-in hybrids. Now, when we look at the impact of electric vehicles on your energy consumption, and consider these factors when it comes to energy planning, we shouldn't actually consider our hybrid electric vehicles. So even though we say we had 10,000 electric vehicles in 2022, there's only 1,357 which we would have been worried about or interested in terms of these guys and possibly the plug-in hybrids that would charge their vehicles. So in the simulator, I mean, if we look at the 2022 story situation in terms of the number of vehicles, that's about 0.15% of your national internal combustion engine vehicle park in as far as your passenger vehicles are concerned. But in a simulator, what we could do then is, we can include or we can run different scenarios to say, listen, what if we had 20% EV market penetration? If we had, 40%, and we are charging them in a particular manner. So we can change when we want to charge and how many hours and the frequency between charging and so on, and then run scenarios like that to understand then what the impact would be nationally. But also we can say at this stage, we set it at 80% of the vehicle is being charged at home. You can change it to 50%. So I think UCT used assumptions of like 50% at home for one of their studies. And then what you could also then do is then let me go to once you have that. Right, sorry, I just got a lot going on there. You could then also introduce solar PV nationally, choose a particular system and say, listen, what fraction of your quintile 4 has solar PV, and similarly for your quintile 5. This value, 5%, it is not validated. It was just used to run a scenario, or it could be 10%, or it could be 20%, depending on what you want to see, and then try and understand what impact that would have then on the load that Eskom sees. And so I think I'm going to stop there with that particular with the. Okay, let me just close it like this. This new Teams is a bit interesting. So I'll go back to the slide pack, full screen mode. And this is basically then the results that were generated. I essentially exported them from the simulation into Excel, because Excel draws prettier graphs than my simulator. And these are typically the kind of results that we can get then from the simulator. We could then calculate cumulatively for the single household what we're looking at in terms of the different quintiles and the kilowatt hours, and look at then the seasonal impact. When we changed our charger type, if we use a level 1 charger, then you'd have the base consumption curve is this blue one, which is now hidden at certain points. And then when we start charging our vehicle, the green one is a level 2 charger, which then takes into account also the battery size in terms of calculating for how many hours we'd be charging the vehicle. Actually didn't show that one. Sorry, just gonna quickly show that one. When it comes to EV charging. So here we can actually choose whether it's a level 1 AC charger or level 2 AC charger. We can also change then the kilowatt of that charger, and depending on the charger that we choose, as well as which battery, which kilowatt hour battery, EV battery we choose, there's a calculation in terms of how much charging needs to take place for that particular vehicle. And so that's basically what we're seeing in terms of the profile. So obviously, the profile we're seeing is dependent on a whole bunch of assumptions. And then some of the assumptions on a national level is that 40% of the vehicles will be in quintile 4, 60% in quintile 5, because we assume there's a higher number of vehicles per household in your high income groups, and various other assumptions. Here again, this is when we ran scenarios to shift the starting times when we charged our electric vehicles. Here's when we charged, this is our base curve, and then we decided we're going to charge at 6 p.m. And we ran another scenario at 8 p.m. and then another one at 10 p.m., another one at midnight. That was for quintile 4, and then we did similar things then for quintile 5. And here what we're looking at then is what happens when you change the charging frequency. So this is your small electric vehicle battery capacity. This is your medium, and then this is your large, as I showed you previously. And then if we charge it every day, this is what we're looking at in terms of the additional kilowatt hours. And this would then be every 2 days. Here, this is over a period of a month. If we look at, say, quintile 5, for example, there's a whole lot of results that were generated, which is included in a report that Aletta will be signing off soon, I hope. And then these are just a few of the results which I picked out just to show you the sort of results that we got from the study. So when we look at the cost, and this is based on the time of use charging, when it comes to your quintile 5, we'd be paying in January an additional 53 Rand, 78 if we charged our vehicle with the charging pattern that we assumed. Obviously, if you change that charging pattern, it's going to be different. But for this particular set of results, it was run with that assumption in mind. And then if you charge it at like 8 p.m., it's 38 Rand. If you charge it at 10, it's 32. And then at midnight, it's 31. So then you can have the discussion, are people likely going to wait until midnight to charge if they're going to just save a few cents moving from a 10 p.m. charge to a midnight charge? And if you look at this, then the incentive might actually be big enough for people to say, okay, I can save uh, a fair amount if I do move from a 6 p.m. Charge to an 8 p.m. But the dark question is, if you look at those income groups where they're getting their income from other investments, and it's not necessarily just the disposable income that they have through salaries and so on, they most likely won't really move their charging behavior based on cost. A lot will be linked to convenience. When we look at the single household, this is the kilowatt hours here that we had. If the blue bar chart indicates your base, and then your purple one is what happens when we start charging our electric vehicles. This is cumulative over each of these months. And then we introduce a 3 kilowatts system, PV system, calculate then the energy that's actually met by the solar PV system that then Eskom is no longer supplying, and that's why it drops. It's from an Eskom perspective. However, if we have solar PV and EVs being charged, then this is the situation. So we do actually end up saving a fair amount from our original cost, and that we would, sorry, it's not cost, your energy impact, but also then the cost. So this is on a national level in terms of the gigawatt hours. These are also the simulated values. They are relatively close in terms of what the actuals would be for the previous year. Here again, we ran scenarios. These are the 2023 values in terms of the sales for your electric vehicles. And you'll see that despite load shedding, it doesn't seem to have really affected consumers in terms of whether they would want to buy electric vehicles. So that's an interesting dynamic. This is where we ran different EV market penetration rates that said, 10% to 20 or 30 or 40% would be charged, not charged, but we'd have that value in terms of the number of full batteries and plug-in hybrids that would end up being charged in quintile 4 and then this number in quintile 5. And then if we look at the national picture, at a 40% EV market penetration rate, this is only about 0.5% of the total national residential consumption based on the charging behavior that we saw and the assumptions that we used. Obviously, this could change if we use different assumptions. And then when you look at your sales, this is only perhaps for Eskom an additional 0.34% more that we could get if people charged their EVs at home. And then in terms of your solar PV, various scenarios were run. Assumptions whether there was the 3 kilowatt in your quintile 4 and your 5 kilowatt in your quintile 5, and then at these various penetration rates, we said you could, at a 40% PV market penetration rate, look at an additional almost 5,000 gigawatt hours additional in the residential sector. And then this could be about 10% of your total national residential gigawatt hours. Year calculations were then done using different petrol fuel types and then diesel fuel types to calculate. This is based on one full tank, not even a full tank. It's actually based on 250 kilometer range with 7.5 liter per 100 kilometer fuel efficiency values for your petrol and your diesel vehicles. And then calculations were done to say, for the same distance, if we then charge at a very expensive public charging DC station or an AC public charging station, or, if we just charge at home over a period of a month, that's possibly what we're looking at. And so, you find it is a hell of a lot cheaper than what you would pay for the other fuel types. And then in conclusion, we think that if you charge at 10 p.m., there might be a little bit of a financial incentive, but not a fantastically large gap between like 10 and 8 p.m. charging. So we suspect that if there's a shift in terms of charging behavior, it would most likely be people moving from the 6 p.m. to the 8 p.m. Peak. And this is basically saying what I said before. And so, yeah, so that's it. I think that's all I have on my side. Any questions?
Thank you very much for a fantastic presentation. I'm just a bit concerned that we have an impossibly short time to do it justice. From a questions point of view, I've got a million questions, but let me not be selfish. Folks in the audience, If you have questions, raise your hand, please. Okay, I've got Wayne up. Wayne, you're first, then Lugile second. Go ahead, Wayne.
Thank you, Nalini. This was excellent. It was, yeah, I'm very impressed, and it is great research. I want to know if, just firstly, just an observation. Like these EV chargers are, they even if the domestic and domestic chargers can even optimize the charging based on the tariffs. So it is something that the customer doesn't even have to think about in many cases. So even if it's only saving a little bit of money, I think we might find people opting for that. The other question I have is have you considered demand response? Like if you can remotely switch off the chargers or throttle the charging from a signal from the system operator, maybe to reduce your demand on your system when there are constraints.
No, it hasn't been built into the simulator. That was not one of the dynamics we looked at.
Okay, thank you. Yeah, it's almost like any question you're going to ask now will probably take at least half an hour to clarify because of the questions that follow. Lungile, you're next in line. Thanks. Next in line.
Thank you so much. Thank you for that presentation. Absolutely amazing. The question that I had was linked to what Wayne was, asking around that capability of systems to switch off as and when, or perhaps to optimize your charging on your behalf. But it's not necessarily have you built it into your system, but is there an availability of such in the market if you are aware? So that's the first thing. The other questions I have are very detailed, and I'd rather I've already sent you a LinkedIn invite. So I'm very, very, excited. Thank you very much.
All right.
Yes.
So I think the first question, Aletta is better positioned to answer. I will actually put down, if that's okay, my email address in the chat, and then I'll be able to answer the other questions, hopefully in a lot more detail. Aletta, are you aware
Yes,
of anything in the market?
Thanks, Nalini. Yes, in terms of demand response, it's something that we are looking at on the distribution side as part of the distribution system operator. So it's not something that is finalized, but it's one of the options that we are looking at. And that is, I think our colleagues know that we have been in talks with the Danish Energy Agency to see what can we learn from them in terms of managing EV charging. And those are some of the things that they've shared with us, where you have an option via an aggregator to actually pause charging maybe for 15 minutes while you stabilize the system. So that is something that we are looking at. And then another option then is the vehicle to grid, which is actually still part of research, and it's also not enabled from the OEM side. So in the long term, it's another option that we are looking at. Thanks.
Yes, thank you. Certainly, it would be unwise to have an uncontrolled elephant on the system. This is something that we're hoping for. Vasu, you have a question? Go ahead, please.
Yeah, hi. Thanks for that very insightful presentation. So I just wanted to check from a project point of view. Then you've got your different scenarios. How do you then go about using that information for planning purposes, and does it then get fed into other let's say like excellent models and so on?
I think that's mostly on the strategic planning side. I'm not sure if Aleta, you as the customer would be able to answer exactly how the results are then used on the distribution side or Eskom wide.
Yes, currently we are using it for strategic planning to understand the impact of EVs in the different customer sectors. But in terms of network planning, yes, it is going to be used as input, because one of the, what can I say, the initiatives that we are running under e-mobility is actually skills development, and also looking at modeling and planning in terms of load forecasting for EV charging. So there is a big initiative that we are running with network planners, where we are using all this data as input.
Okay, thank you.
Yes, certainly. And this is something we picked up from EPRI as well. It's the technologies arrive and the skills have to build up, and then one can say that you can exert control, and the tools then must go out, and so on and so on. And that's how we end up having predictable behaviors on the networks. Nalini, if I can ask a question.
Yes, good.
I think one of the interesting things about the PV systems and possibly the EV charging systems as well is that they seem to have kind of defaults set into them, which are, you can call them business rules or something like that. How did you handle those kinds of issues? I know that you said that there were PV systems of different sizes, and I guess with EV systems of cars of different battery capacity, there might be different rules built into them as to how they handle the recharging.
I'm not sure if I know what you mean in terms of these rules, like in what way?
Sorry, it's basically defaults about how they behave, and then the user can pop in and adjust the system behavior to suit their personal circumstance after that. But they're delivered behaving in a certain way.
So yeah, I still don't understand exactly what you mean. So when you say they delivered with default settings, that's your charger in terms of the specifications.
Yes. For instance, the maximum charging current and when they will take a sip from the distribution system. What's the minimum level at which they start charging from, things like that.
Because in the
Obviously,
simulation,
it very much affects how they behave on the network, and the way to control the standards is either to change the default to when the systems arrive, or to almost try to post control that at an aggregator level. Thanks.
Okay, so in terms of what I've built, I haven't actually looked at the hardware aspects. So I've just assumed that, listen, the only dynamics that I need to worry about is what my residual capacity in my vehicle is, and my the charger kilowatt, and then I calculate just charging hours. So I don't actually look at any of the default specifications for the hardware side of things. Aleta's got a hand up. Perhaps they've looked into that area a bit more than me.
Go ahead, Aleta.
Okay, thanks. Yeah, according to my understanding, that is actually managed via the back-end software that the EV owner will have. The EV owner will have some kind of an app on their cell phone, and they can be able to control the charging. I think currently for private vehicle owners is something that they can do privately on their cell phones. But for example, fleets, because there are some companies that are managing EV fleets in the country. If a company is managing your EV fleet, they can actually control that for you remotely. Just checking the level of charging on your vehicles, and then their software will ensure that the vehicle will charge automatically when the charging level is when the battery level is at a certain percentage, and then stop when the battery is fully charged, or you can decide to stop it automatically when it's 80%. So there are companies that are doing that, but I think for individual consumers, we are not there yet. But it's something that we are looking at. Also something that we are learning from our European counterparts, where in those areas, if you are a residential customer that owns an EV, that can still be managed by your aggregator.
Yes, certainly the biggest problem with appliances is customers, isn't it? Thanks, folks. Do we have Wayne? You have your hand up. Go ahead, please.
Yes, sorry, I have another question. I want to know if now this could be either Nalini or Aletta, if you have considered the effect of your loss of your system diversity when you're, especially after load shedding, but also maybe at the time of your time of use tariff boundaries. Like there will be an incentive for many vehicles to start charging at the same time, and your network was maybe designed to a 4 or a 5 kVA ADMD, and then suddenly you find that your ADMD is closer, it's higher, and you overload your system. You could trip your feeders, etc., which already happens after load shedding.
Yes, certainly. This is one of the points that came out recently from Britain, talking about the loss of diversity by tariffing. Nalini, do you have any comment?
So on my side, I must make a declaration up front. I'm not an electrical engineer, and I don't understand much about the lines. That's why we also have a letter here. But in terms of the simulation, that was something that was discussed in terms of when, it's a post load shedding. There is that, okay, I'm using layman's terms, that surge in demand, because you have all the inverters kicking in and your batteries charging and so on. But in terms of the simulation, that wasn't actually built in. And in terms of the impact on the network, the best that I could contribute to is to say, listen, this would then, if people shifted in terms of the time of use charging to a different time, this is most likely the loads that we are potentially talking about, and then what that impact on the lines and that sort of thing. That would be, I would not know. Alita, I'm not sure if there's anything there that you could add.
Okay, thanks, Nalini. I think, as mentioned from our side in distribution, it has been raised as a concern currently with load shedding. Just not looking at specific EV load yet, but just looking at that surge that you mentioned after load shedding. And what we are doing now with the rollout of smart metering, we are actually talking to our smart metering suppliers to see if we can be able to stagger in the load, the return of the load, not to switch on. You can switch on the feeder, but for the meters to actually do that automatically, managing that diversity, ensuring that not all customers get switched on at the same time. So it's something that we are still working on with one of our metering suppliers. We don't have a solution yet.
If I can interject there or ask for clarity, That was one of the concerns with introduction of EVs in South Africa. How would they work with various kinds of smart metering? What I'm hearing is that the details of that still have to be worked out. This is particularly for smart metering where the possibly the current limit is lowered as a load shedding avoidance technology. Can you confirm that?
Sorry, can you clarify the question regarding smart metering?
The smart metering, we've heard where the current limit is adjusted as a load shedding avoidance strategy. What I'm hearing is that the interaction between that and EV still has to be worked out. There may be interference there. Is that correct?
Yes, that still has to be worked out. Are you talking about the load limiting initiative that we currently have?
Yeah, the pilots in Joburg with the where the load limit is lowered to avoid load shedding during times of high system demand.
Yes, I think even with the EVs that will be built in, because during load limiting, the bigger loads are actually automatically off, and that will include EV charging because it's one of the biggest loads in the households. So when we stagger, once we finish with that software that will stagger in the switching back of the load, it will incorporate the entire household load because the EVs are currently, well, in Europe, they are able to separate them, but currently we don't separate it from the household load. We have 1 meter per household.
Yes, yes. Well, thank you very much. From those in the audience, are there any more questions? We're down to final round now. If we can
Marcus,
see hands
from
for
my
questions.
side, sorry, I didn't raise my hand. I just wanted to just say that what we are seeing now is that the load is no more passive, but the load is becoming more dynamic. And because of that, even planning, it has to adjust accordingly. And this is why earlier on, when we were talking about the future customer as well. So these are some of the things that we will need to consider. And that's why this project that Nalini and Naleta actually embarking upon is very much important for planning, for network design, and all of that. When you look at tariffs, for now, because of load shedding, we are talking of load limiting capabilities. But as soon as load shedding, it's no more there. There are other things also that this need to be looked at. So the dynamism of the load is something that is critical. Looking at the inverters, the EV itself, because it's having a battery pack inside the house. When you have a PV panel, you will also be having, if it's coupled also with a battery inside the house, and with a grid-tied connection as well. So this dynamism of the load is very much important for us, particularly from the point of view of load research. There are some gaps that we have identified, and we need to find a way as a team of how we can be able to close some of those gaps. The issues of the ADMD, which were raised by Wayne, there are gaps that needs to be looked into. Even the standard itself at its current state, Marcus, as you are aware that we are also trying to look at the standard to make it, the SANS 507 standard, to make it more practical and relevant to the customer or the future customer that we are perceiving to have in the future. So all of these things is a package, and ESCOM alone cannot do this. Obviously, we need to have on board other stakeholders. Thank you, Chair. And a big thank you to Aleta and Nalini to allow themselves and me to share the results with us. Marcus, not taking the words from your mouth. Thank you so much.
Just from my side, I just want to share a thing that may be of interest about where to from here. Nalini, if you can, you said that you were busy calibration phase of the model. Where do you see the work going from here? Can Can you see that image?
Yes, we can see
Okay.
it. So we could then, it's actually in the model testing.
Okay.
And model testing side, we could run various policy assumptions through it. We haven't done that yet. But in terms of running the scenarios and having those engagements with people and discussing the results and so on, that has been going on in the last month or so. Once the model is finalized and we've already got the initial scenarios and so on, then Aletta and her team would be able to take it further in terms of understanding then the impacts under different assumptions and with the different scenarios. So it's more kind of between model testing and policy evaluation. However, the knowledge translation is something that I think is kind of integrated in there somewhere. I mean, you learn as you actually develop the model as well, and as you engage with people. So it's not something that happens at the end, kind of thing only.
Yes, certainly the great value of modeling like this helps to align thinking of a number of people that is important to carry the issue forward. And this walk and talk is exactly what you're doing with the alignment. Just from my point of view, just listening to you today sounds very much like listening to somebody present an IEP. The breadth and the detail of the modeling is just it is amazing to look at, and I wish you all the luck with where you're going with this in future. And from my side, thank you very much for presenting to us today, and it is very much appreciated. And if you do have a follow-up session with admirers from this group, please include us in that invite.
Thank you so much for the invite, and thank you to Aletta as well for attending. I think she had more questions to answer than I did. I'm very glad she was here. But to anybody else who wants to know more about the model development side and the simulation and what I've demoed, you are most welcome to email me and engage further. Thanks.
Yes, certainly. I would encourage the folks in this audience to have a look at Nalini's system dynamics modeling chapter, and if you can at all, get some knowledge there and participate, because it looks like it's a very capable tool if it's capably driven, as we've seen today. So thanks everyone for sitting in, and once again, thank you so much for the presentation. It's been amazing. Okay.
Thank you.
Okay, thanks Aletta for joining us, and for those in the audience for your great questions. And I'll end the session now.